Hi friends, in this video we'll see what is modulation and its necessity. In general, no signal is a single frequency sinusoid. Actually, it spreads over a range of frequencies called signal bandwidth. Now we'll see what are the limitations using a unmodulated wave. First of all, the limitation is size. In the last video, we have discussed that the size of the antenna should be comparable to the wavelength. That is, it should be at least lambda by 2 or lambda by 4, something like that. Okay, if you are using a wave of 20 kilohertz frequency, what will be the wavelength? Speed of wave is equal to wavelength into frequency, right? So this will give us the wavelength to be 15 kilometers. Building an antenna of this size or even half or even quarter of this size is not practical. So let us see what will happen if you are using a wave of higher frequency, that is say 1 megahertz. Then the wavelength will be 300 meters. Okay, this is large, but we can build right antenna of this size or half of it, quarter of it. So here we are seeing a need of translating the information contained in our low frequency signal, that is low frequency band based signal, into high frequencies. Before transmission, band based signal is nothing but a message signal. This is one limitation, right? Other is that it is power radiated by antenna. Because of theoretical study, we know it to be proportional to L by lambda whole square, where lambda is the wavelength and L is the length of antenna. Now what can you say from that? If lambda is less, we'll have more frequency, you know that, right? And more frequency means more power. So you can say that transmission is done well. So here also you are seeing the need for higher frequencies. And other thing is that if you have many transmitters and they are emitting information or waves simultaneously, they get mixed up. This shouldn't happen, right? And what is the solution? The solution is that you have to use communication at higher frequencies and allocate a band of frequencies, and each band of frequencies to each message signal. If you allocate in that way, then this clash doesn't happen. So in simple words, we are taking the help of high frequency signal and attaching information to it. That's it. This process is known as modulation. If C of t, this is your wave, say, represented by AC sine omega c, that is the angular frequency, plus phi, say. This is the initial phase, right? Phi is the initial phase and omega c is the angular frequency and AC is the amplitude. Now you can modulate any of these three, amplitude or angular frequency or phase, and each of these will give different types of modulation. This will give you amplitude modulation and this will give you a frequency modulation, that is FM, and here you get PM, that is phase modulation. Out of these we are going to discuss AM, that is amplitude modulation. If this is your wave, C of t is equal to AC sine omega t, omega ct, and you want to modulate it with this wave. So let this wave, that is modulating signal, be AM sine omega m t. So when you superimpose these two, you're going to get the modulated wave as CMT is equal to AC plus AM sine omega t, omega mt actually, and this is to be multiplied with sine omega ct. So this can also be written as, when AC is taken common, 1 by AM plus AC, and the same terms come here. Now why am I writing like this? Because this AM by AC, I am interested in that. That is actually known as modulation index. So this is modulation index and that is represented by mu, and it is normally less than 1 to avoid distortion. So writing the same formula in terms of mu, we can write it as this one. This is the formula in terms of mu, that is modulation index. And note that here you have sine of some angle and sine of other angle, right? you have a trigonometric identity which says 2 sin A sin B is equal to cos A minus B minus cos A plus B. So applying that here, you can write the same formula as this one. This is your final formula in terms of cos also. Why am I writing like this? Because here you are able to see that you have omega c, one frequency, and you have omega c minus omega m, and other frequencies omega c plus omega m. These are the three frequencies that you got in this final modulated wave. This is known as lower side frequency, and this is known as upper side frequency. When you plot the amplitude with respect to the omega, that is angular frequency, this corresponds to AC, right? This is amplitude of this carrier wave, and this corresponds to omega c minus omega m, and here you have omega c plus omega m, and here you have omega c. So this amplitude, which corresponds to the lower side and higher side frequencies, should be equal to this one, right? Mu AC by 2, as we have seen in the above formula. Obviously this will be less than AC because mu is less than 1, right? Solve this problem. A message signal of frequency 10 kilohertz and peak voltage 10 volts is used to modulate a carrier of frequencies 1 megahertz and peak voltage of 20 volts. We have to find the modulation index, that is AM by AC, right? That will be equal to AM is this peak voltage is 10 and here it is 20. So modulation index is 1 by 2 here. And second part, the side bands. Omega C is nothing but 1 megahertz, right? So that will be 1000 kilohertz, and omega m is given as 10 kilohertz. So my lower side band, that will be equal to omega c minus omega m. So 1000 minus 10 kilohertz, that is 990 kilohertz, and upper side band will be omega c plus omega m, that is 1000 plus 10 kilohertz, that is 1010 kilohertz. These are the two side bands. Let us see how a amplitude modulated wave is produced. First of all, you need to give this modulating signal, right? M of t, that is, say this one is am sine omega t, omega mt, and you have to combine it with your carrier wave, that is AC sine omega c t. So when these both are added, you are going to get xt. That will be what? It will be am sine omega t plus AC sine omega ct, right? Okay, let me write that also. Better is better. So this will be the xt, the combination of m of t and c of t. Okay, square law device is just a non-linear device which takes the input as x of t and gives the output as this one, b x of t plus c x square, that is where b and c are constants. Just understand that if input is x, you're going to get the output as bx plus cx square, where b and c are constants. If you put this x value inside this function y, you are going to get the result as this one, this big function. You just have to expand it, and note that in this y there is omega m, there is omega c, and there is 2 omega m, there is 2 omega c, and there are these frequencies also, omega c minus omega m and omega c plus omega m. So there are many frequencies. That is why we are using something called as band pass filter. Band pass filter is nothing but it just filters and gives us only required frequencies and cuts off the other frequencies. And if this is your band pass filter, so this will cut off all the frequencies which are lower to certain value and higher to certain value. These values you can decide it, of course, and that is the function of band pass filter. So through this, after passing through this, you're going to get only these frequencies, omega c and omega c minus omega m and omega c plus omega m. So these are the three frequencies that will be left out after passing through the band pass filter, and finally you get the amplitude modulated wave. Now let us see how amplitude modulated waves are detected. First of all, this is the receiving antenna. So you receive signals from this antenna, and they will be very less, or they'll be very weak. So you need to amplify them. That's why you have amplifier here, so that they'll become strong. And next you have something called as IF stage. That is, carrier frequency is changed to a lower frequency for further processing before detection, and this is known as if stage, that is intermediate frequency stage. After that you have something called as detection. Detection is the process of recovering the modulating signal from modulated carrier wave. That is, it is just the opposite of modulation. And finally, after this detection is done, your wave will again be weak, so it needs to be amplified again. So you have amplifier here, and finally here you get the output. This is how detection is done, and that's it. Bye.